Okay, now that we have established our displacement vector, we can move to calculate the strain tensor. Strain tensor, which is given as and we have ui as minus z dw dx 0 and w as a function of x. So this is our u, this is our say ux, uz, and this is uy, which is 0. Three components of the displacement vector. Okay, so easily we can calculate our strain tensor, and I write it here one by one. The first one is E11 or EXX in our coordinate system, and that is 1/2 of du. Don't want to repeat the subscript for the vector du dx, and again du dx. So 2 therefore is du dx. Yeah, I have to differentiate the x component of the displacement with reference to x. So z comes out as a constant, and this becomes d2w dx squared. Okay, because you have to differentiate with respect to x, and w is just function of x. I can turn the partial derivative to total derivative, and this is the results. Now, if I go to the other components, the second component, which is the derivative of u with respect to y, because j becomes 2, and derivative of y respect to x is 0. And now we come to the third one. So third one is axz, which is equal to 1/2 du, which is x du dz plus dw dx, which is 3 to 1. Now this becomes what? Du dz is minus dw dx, and dw dx, so this is this, and this is plus dw dx 0. That is a very important conclusion in Euler beam theory, that this xz, I will explain it. Let me write the rest of the component, is 0 actually. And if you go and calculate the rest of them are 0 for symmetry, and of course if you calculate it directly, everything else is 0. The only component that survives is this component. The rest are 0. Let's look at this one before we move further. What is this string? So if I come and draw my cross section, This is my x, this is my z, this is my beam. So here I am saying that this is xz. So it should be on this plane, which is normal to x, and in the z direction. So this is my exz string tensor component. So we are saying this is 0. What does it mean? It means there is no shear strain. And obviously for the other one, and there is no shear strain, both of them are 0. The only component of the strain that survives is exx, which is minus z d2w dx square, dx2. The rest is 0. That is a very important conclusion. We have to realize what the implication of this is. What we are saying is that from the kinematics assumption that we had, these two assumptions, that he usually simplifies these two assumptions, that he usually simplifies the calculation of the displacement, which is a translation and rotation basically of a rigid plane at each cross-section location, we get the result that our strain tensor has only one component. And more importantly, probably, is that all the shears are 0. And also should point out here that if you calculate E22, which is EYY, which is UY with respect to Y, is 0 because U is 0, and this is 3 is also 0 because 3 you have to differentiate the W with respect to Z, which is not a function of Z, again is 0. So be careful about that. That is the only component that survives, is the EXX. So what is actually this guy? This is the strain due to bending only. So we are saying that the shear is absent in Euler-Bernoulli based on the kinematics. So based on kinematics assumptions, shear, strain, and obviously stress, as we will see it, strains, strain components are null. Maybe you say in the cross section, in a typical cross section, in any cross section. Right? And only normal strain, which is due to bending, is non-zero, assuming that there is a slope. Now, one thing that I would like to point out here is also the sign of this d2wdx. This is actually the curvature, or the inverse of the radius at the point. So if I look at it here, in a schematic way. So if you have a beam like this, that you have positive, this is positive bending moment, positive, positive. So this deflection, if you like, has a curvature. Uh, has a curvature, which is the curvature of the radius. The curvature is d2 w dx. It's some approximation, of course, because it is small. And what I wanted to say here is that if you have a curve, this is your elastic curve, therefore your dw dx slope here is positive because you are going in the positive x direction. And so this is my beam, this is my x, and this is my z, and my z is increasing, so this is positive, whereas here is negative because as x increase my w decrease, and therefore it's negative. But therefore my d dx, the change in my slope, is what? Is a negative value, which is dw negative, minus a positive value. You have to consider it this way because x is positive. And then this is divided by dx, but this is what? This is negative. Therefore, curvature is negative. And again, if you have a negative moment here, this is negative moment, then the curvature is positive. So in here is positive, here is negative. Consider that, and we will come back to it when we discuss the moment curvature relationship later on. So as a conclusion here, I would like to box it that for our coordinate system, for positive moment, we get negative curvature, and vice versa, meaning for negative moment we get positive curvature, as I explained here. Okay, so this concludes I'm sorry for interruption. I was saying that this concludes the kinematics, because we consider the displacement based on the assumptions. We got our displacement, and then based on our, this is the u component, and the v is 0, and w is simply the coordinates in the z direction. And then based on that, we consider the strain, or calculated the strain, and we came up with a very important conclusion that the only strain component that survives is E11 or EXX, which is the normal component of strain to the plane which is normal to x-axis. Also important that the shear component is 0. And I would like to point out here that this is 0 exactly because of the assumption, because we are saying that the rotation of any cross section at a given point is exactly the same as the slope at that point. So therefore, this quantity are equal, and that gives you 0. So there is no way from that assumption that you get a non-zero shear in Euler beam theory. That is why Euler beam theory is famous for not considering shear deformation or shear deflection due to shear. Okay, now let's move on to the calculation of the stress. And as we know, the stress is given in terms of Lam's constant lambda, as shown here, and we discussed it before. Now, I will use maybe I use it with the Lam's constant, but I will relate these things to the more common constants, which is Young modulus of elasticity and Poisson ratio, and of course shear modulus of elasticity, which is this mu here. This is shear modulus of elasticity also. But let's focus on the main points here rather than the constants. So what is sigma 1,1? Sigma 1,1 is sigma x, which is the stress normal to the plane perpendicular to x-axis in the direction of x-axis. Okay, so this becomes I and j are 1, both of them. So delta 1,1 is 1, and therefore this becomes lambda. EKK is summation. And plus 2 mu E11. Now, this is 0. This is 0. These are the diagonal elements of our strain tensor. We had it here. Yeah, this is this element and this element. So this is 0. Remember, the only one survives is E11. Anything else that shows up, we give it 0. So we have E11 and E11. So this becomes E11 or EX, I write it, lambda plus 2 mu. E12 is 0. If you calculate it, E13 is 0 because shear is 0. It is symmetric, but I write it here, is 0, but be careful. E22 is not 0. Sorry, sigma 22 is not 0, although E22 is 0. That's a very interesting conclusion here. And that is exactly the result of this term. So if I write E sigma 22, which is sigma y, y, but I just sum it up to y, is what? Is lambda delta 22 is 1, but again I get E11, E22, E33, so only E11 survives, and plus 2 mu E22, right? Because this is 2. So this is surviving EKK, and this is 2. But E22 is 0, right? So this guy survives. And that is what? That is equal to, if I write it here, is, well, I leave it as is, and maybe I just change this to ex. Okay, and this is 0. This is our matrix. This is 0. This is 0. And again, this one comes out as Ex, similar to sigma y. So this is sigma z. So what are these? Let's make sure that we understand what is going on here. So again, on a cross section of the beam, we have x, we have z, and we have y component coordinates. Now, if I change color to be more distinct here, so this one is the stress in this direction. This is sigma x. Sorry, I dropped out a 0 here. There should be a 0, another 0 here, and maybe we don't need this. Okay, so the second one is 0. The third one is 0, which are the shear. And what is this? This is the normal to the y direction. So there is a there is a stress. There is a stress in, maybe I want to change color here to be consistent. There is a stress in this direction, which is normal. So this E22 is the stress normal to the surface or plane perpendicular to y-axis in the direction of the y-axis. So this is sigma y. And similarly, this is the stress at this plane here. So this is sigma z. These are lambda Ex and lambda Ey. Sorry, Ex. So, but we will see that these two will be very small when I write it in terms of Poisson ratio, and I will do it soon. But let's make sure that we understand this. The only component that in terms of magnitude is important is this sigma x. The other two comes because of the Poisson effect, which is the stress normal to the any plane in the y direction and stress to the plane normal to the z direction. And these two also survive. Now, in the relationship between lambda and mu, which we call it Lami's constant, we have more meaningful physical constants, which is modulus of elasticity and Poisson ratio, mu and E. This can be shown that these two are related, or these four are related to each other like this. Sorry. Okay. And I have a coefficient here that I get lambda plus 2 mu is equal to actually E 1 minus mu divided by 1 plus mu 1 minus 2 mu. Therefore, my sigma ij or stress tensor will be given like this. I will write the Ex here as we have it, which is my Ex is what? Is minus Z d2W dx2. So this is minus Z d2W dx2. This is 0, this is 0, this is 0, and my sigma yy is actually mu e divided by the same denominator, Ex again. I write it to be consistent, but we will drop it due to its small magnitude. These two are the same because the only term that survives from EKK is EX. EY and EZ are 0, therefore, and you see that how simplified is calculation based on the Euler-Bernoulli assumptions. Now, as I said here, E is modulus of elasticity or Young modulus of elasticity, a constant, a material constant. And mu is Poisson's ratio. Basically, the ratio of strain in perpendicular direction. Usually, this guy could be considered very small. It is usually 0.5 to 1 maximum. So if I consider the Poisson effect 0 here, therefore this term, if Poisson effect is neglected, this term becomes 1, right? So mu is 0, this is 1, and this term is 0. So again, assuming mu is negligible for some materials, then you will not get the normal stresses in the y and z direction. The only one that survives is in the x direction, and as you see here is given. So if you have a material that you cannot ignore those or even if you don't consider mu 0, you see here that mu is directly multiplied to e here in this term, and in this term, and mu is very small compared. So this is a very large number. So it multiplied by a small number. So this quantity here, the stress, will be much smaller than this, even for a non-zero Poisson ratio. But we assume, just for the sake of this, that we can drop Poisson effects compared to the strain that we have in the x direction, very small in the other directions, and therefore we can say that we almost assume it doesn't exist. So it's a kind of relative order of magnitude of quantity that we are discussing. Now, the main important part is also here that there is no shear, no shear, no shear, no shear stress. More importantly, this one, as I explained here, because this is your sigma, in this direction, this will be the similar stress when you multiply it by E becomes sigma x. So if I want to conclude here, and if I draw the cross section of the beam here, so this is Euler-Bernoulli theory or beam, and mu is very, very small, almost zero. The only stress that you have is sigma x, which is minus E d2w dx square. Sorry, I missed a z here. There is a z here. So let me rewrite this. Minus z d2w dx square. So we got this relationship using our kinematics to kinetics map. Stress belongs to kinetics because it needs some material property and constitutive relation as shown here, and therefore this is our relationship that we have here. Before going further, let's see the properties of this stress. So sigma x is only for a given section. So x is given, x is fixed, is only a function of z, assuming E is also constant. So let's say that sigma x is a linear function of z. That's the first one. Second, sigma x is proportional to the curvature. I mean, at a given x section or cross section. These are two very important points here. Now, if you come here and say, okay, let's see what these things does, and if I come and draw a quick sketch here, maybe I do it right here. So above here, above the x-axis in the direction of z, I have negative z. So for a negative z, I get some stress that linearly varies to 0, because at neutral axis z is 0, and we said that this varies linearly from this equation. So this, and then for a positive z, this becomes negative. Therefore, this is my reference line here. So at negative, I took this compression, so therefore will be tension in this direction, or vice versa, doesn't matter. The main point here is that you understand that the variation of z along z is linear. sigma x is a linear function of z. And that is exactly what we have in pure bending for Euler-Bernoulli. And that is a direct consequence of the kinematic assumption, and we get the formula here.